Now we will discuss one of the most important topics in DC machine and also one of the most feared topics, right? So first we will see what is meant by, what is the definition of commutation. So commutation is nothing but the process of converting the AC voltage and the current to DC voltage and currents, right? In DC machines actually alternating current is being produced, but by using the commutator and the brush system we are able to convert into a DC voltage and current. So you can write it is the process of converting AC voltage and current. So here AC itself means alternating current, right? But colloquially we just to differentiate between AC and DC we write AC voltage and current, okay? So AC voltage and current to DC voltage and current, okay, by means of a commutator. Now in practical machines commutation is hampered by two problems, okay. So the first one is the armature reaction and the second one is the LdI by dt voltage. This will occur due to the inductive nature of the winding. So we will discuss both of these problems one by one. First we will start with the armature reaction. We will consider a two-pole machine. This will be the north and south pole, and here in between there is the rotor. So if you consider this as the top view, then the windings you can show like this. Now what will be the direction of the magnetic flux? The magnetic flux direction will be from north to south, right? So you can take this to be the field flux. Now if you assume that it is a DC generator. So in a DC generator what is happening? The mechanical force is given and the machine will generate voltage, right? So we will assume that the rotor, it is given a counterclockwise direction. Let us take this angular velocity to be omega. Now if you consider the conductors which are under the south pole, we will consider this conductor, okay, that which is directly under the pole. And what is going to happen? We'll draw it separately. Here there is a conductor and the magnetic field is in this direction, right? This is direction of magnetic field, so we will take it as B bar. Now what is the direction of velocity? The velocity, it is, if it is in the counterclockwise sense, then for this conductor, the conductor that is present here, it will experience velocity in this side, right? Upward direction. This will be V bar. So what will be the force, direction of force? If you can do the right hand cross product rule, V cross B, then you're going to get that the force direction is going to be into the plane. So the positive charges will experience a force which is directed into the plane, okay. Then what will be the direction of current? The direction of current is going to be into the plane. So all of the conductors which are under the south pole, they are going to experience current which is going into the plane, okay. And all of the conductors in a similar direction manner, if you do the analysis, then you get that all of the conductors under north pole will have a current which is coming out of the plane, okay. Now what about these two conductors here? So these are at the very top. Now this velocity is going to be in this direction and this velocity is going to be in this direction, which is parallel to the magnetic field. So there won't be any EMF that will be induced in both of these conductors, okay. So the axis that is joining both of these conductors, this is called as the magnetic neutral axis, MNA. So the conductors which are falling in the magnetic neutral axis, they will not experience any induced EMF if it is a DC generator, and if it is a DC motor, then there will be no induced torque. So you can write this point, it is important. The magnetic neutral axis, it is the plane where velocity of conductor is parallel to magnetic field. So for DC generator, induced EMF will be 0 for the conductors that are lying in that on that magnetic neutral axis. Okay, and for DC motor, the induced torque is 0. Next is the geometric neutral axis. Okay, geometric neutral axis. So this is the plane, this is a plane of symmetry between the adjacent poles. So where is this going to be? It is going to be this same axis. Okay, so the magnetic and the geometric neutral axis, they will coincide. Okay, but here comes the armature reaction. Okay, what is the armature reaction? Here we can see that the current will be induced in the armature conductors. Now once current is induced in the armature conductors, there will be an additional magnetic flux. Why? Because a current carrying conductor is going to produce a magnetic field, right? So now in addition to the field flux, there is also going to be armature flux. Okay, in that case the geometrical neutral axis will remain as it is, but the magnetic neutral axis is going to change. So we will see, we will understand why. For that, what we will do, we will try to consider the field flux and the armature flux separately. So this is the north and south pole, and this is the field flux. There will be conductors here, right? We will not consider the field due to these conductors here. Here we are only representing the field flux only. Next we will see only the armature flux. That means there is no field flux. So this will be the rotor and the conductors are going to be like this. Now for a DC generator, so I am reminding you it is a DC generator because the current directions and all will change if it is a DC motor. So for a DC generator which is rotating in the counterclockwise sense, the current directions are going to be like this. Under the south pole it is going to be into the plane, and under the north pole it is going to be out of the plane, and in these two conductors there is not going to be any current. Now due to each of these conductors, if you draw the magnetic field, right? So for example, if you take one conductor whose current is going into the plane, then what will be the direction here? It is going to be in the clockwise sense. Similarly, if you take a conductor where the current is coming out of the plane, then here it is going to be in the counterclockwise sense. So for each of these there is going to be individual magnetic field lines, but when you add up all of these magnetic field lines, then you are going to get a magnetic flux which is something like this. Okay, and what will be the direction? Here this is going to be like this. Here everything is going to be in the upward direction. So you can see that inside the core the flux is going in the upward direction. Now what will be the resultant flux? This here is only the armature flux, right? Armature flux only. Now if we want the resultant flux in the armature, in the core, right, what will it be? It will be the addition of field flux and the armature flux. Okay, so you can, if you draw the vector, then this is the field flux phi f and this is the armature flux phi a. Then what will be the resultant flux? It will be the vector addition. So this is going to be phi r. Okay, so if you draw the core, then you're going to, the flux you're going to get something like this. It is going to be slightly tilted. Okay, now because of this, what is going to happen? The magnetic neutral axis is going to change. Okay, so the geometric neutral axis, remember, it is going to remain as it is. This is the geometric neutral axis, but the magnetic neutral axis, it will be perpendicular to this magnetic field lines. Okay, so it is going to undergo a slight change. So this is the magnetic neutral axis. So this is what we call as the armature reaction. Now what are the effects of armature reaction. The first one is the shift in magnetic neutral axis, right? Shift of MNA. Now what is the problem with that? We will discuss. Okay, this is the first problem, and the second problem is the weakening of flux, field flux. Okay, first we will discuss the shift of magnetic neutral axis. What is the problem if the magnetic neutral axis is shifting? This is the rotor, and here you have conductors, right? Now when there was no current that is flowing through the armature conductors, then where will be the magnetic neutral axis? It will coincide with the geometrical neutral axis. So this is, you can call this as old MNA. When no current is flowing, that means under no load condition, the MNA will be coinciding with the GNA. Now what is happening when current starts flowing? There will be a shift, right? So let us say this is the new magnetic neutral axis. The commutator is basically sliding on the brushes, right? Now when the old MNA is coinciding with GNA, we keep the brushes here, right? Now when you keep the brushes here, there will be no induced EMF in these conductors because they are lying in the magnetic neutral axis, so there will be no induced EMF. That's why we keep the brushes here. What is now happening with the shift? Now these are the conductors which are having zero induced EMF. The rotor is rotating. Whenever the conductor reaches this position, it is having induced EMF of 0. So that means now current is flowing here. Okay. So now the brush is connected at the conductor where the induced EMF is not 0. Ideally, what should happen? The brushes should be collecting the current when the alternating current is at 0, right? But here what is happening? The brushes are collecting the current when the current has not yet reached 0. Okay, so that is the problem with the shift of magnetic neutral axis. So you can write down, because of the shift of magnetic neutral axis, there will be arcing and sparking at the brushes, which will affect the brush life. And this is a maintenance cost, increase in the maintenance cost. Now one possible solution that may come up to your mind is, why can't we just shift the brushes? Okay, but the shift in magnetic neutral axis, it will depend on the armature current. Okay, so at no load there will be no shift. As current will increase, the shift will start increasing, and so the shift will be dependent on the armature current. So you cannot set the brush at one particular position. Next effect was flux weakening. So if you draw the poles again and the rotor, and here the conductors are there. So once again we are considering a DC generator which is being rotated in the counterclockwise sense. Okay, so if you are considering this as the north and south pole, then the direction of current is going to be like this. Right? Now what did we get the resultant flux lines? It was like this, right? Now you can see that there is an increase in flux in this region, while under this pole surface there is a decrease in flux. So on an average you might think that the flux on the whole it is remaining the same. But what is happening? Observe carefully. Here in this region, the flux MMF and the rotor MMF are being added, which is resulting in the increase in flux. Okay, so if you consider the magnetization curve, here we have B and this is H. For a certain distance, for a certain range, it is going to be almost linear, but after that it is going to go into saturation. Right? Now the operation, usually it will be at the knee point, right? And the knee point is where the core, it starts going into saturation. Okay, now when the rotor MMF, this is the MMF actually, when there is an increase of MMF in this region, this increase is not going to result in too much increase in the magnetic flux density, right? This is the increase. Okay, in contrast, the rotor MMF is acting in opposition, right? Then what will be the decrease? This is the increase and say the same decrease, right? Here you can see this and this is same, okay? Now what will happen? What will be the effect on the flux density? You can see that this is now the decrease in flux density. This is the increase while this is the increase. So you can see that this is not equal. That is because the machine is operated at knee point for optimal performance, right? So this means that there is a net flux weakening that is happening because the flux the decrease in flux density is more than the increase in the flux density, okay? So that is how you get the flux weakening. Now what is the effect of flux weakening? In DC generator, we saw that the induced EMF is proportional to the flux, okay? So if flux is reducing, then the generated voltage will also reduce. Therefore, generated voltage will be less. In DC motor, what is going to happen? So the flux weakening, it will actually increase the speed. Flux weakening increases the speed. So why this is so? We will see when we discuss the speed control, okay? So when the speed is increased, then what will happen when the motor is running at more speed? It means that it is taking more load, right? The load has increased. So this means that it will draw more current. This will draw more load current. Now when the load current increases, load current is nothing but armature current, right? And when armature current increases, what will happen to the armature reaction? That will also increase. Armature reaction will increase. And armature reaction was the reason the flux has weakened in the first place. So an increased armature reaction will in turn result to a further decrease in flux, and the cycle will continue like that, and there is going to be a runaway condition where the speed is just going on increasing until the motor breaks down. These are the negative effects of armature reaction. So till now we have been seeing the armature reaction in DC generator, right? If this is the north and south pole and this is the rotor, and the rotor direction is in the counterclockwise sense, okay? Then the shift in magnetic neutral axis, this is going to be in the direction of the rotor, right? So here you can write down shift of magnetic neutral axis is in the direction of rotation. And one more point is, when the rotor is moving in this direction, you can see that it will, if you consider the south pole, then it is going to encounter this pole first, and then it is going to go like this, it is going to leave this pole, okay? So this is called as the leading tip and this is called as the trailing tip. Similarly for the north pole, this is the leading tip and this is the trailing tip. So you can write down this is the leading pole tip, this is the nomenclature, right? Just to differentiate. This is the trailing pole tip. Now the resultant flux, it was like this, right? So now what is happening? This trailing pole tip is getting magnetized additionally while the leading pole tip is getting demagnetized. So the trailing pole tip is magnetized whereas the leading pole tip is demagnetized. So this is what? This is for the DC generator that we have been discussing till now. Now in a DC motor, the opposite is going to happen. So if you consider the poles, this is the north and south pole, let us say. So here the current is going to come first. So if you keep the current directions same, right? Let us say here we got the current directions like this, right? Now if you are taking the same current directions, then the direction of rotation, it is going to change. If you want to keep the direction of rotation as same, then the current direction is going to change. Okay, so either way you will get the same result. This is the current direction. So now the rotation is going to be in this direction. Okay. Now what is the trailing and leading pole tips here? This will be the leading pole tip while this is going to be the trailing pole tip. Since the current direction is the same as previous case, the flux will be like this only. But now this is becoming the leading pole tip. Okay. So the first point is shift of magnetic neutral axis. This is going to be in the direction which is opposite to direction of rotation. Is opposite to direction of rotation. And here the trailing pole tip is going to be demagnetized, whereas the leading pole tip is going to be magnetized. So you can write here, otherwise you will get confused. This is the leading pole tip, whereas this is the trailing pole tip. Whatever we discussed right now, we will try to see in a visual format. So let us say this is the pole, south pole let us say, and this is the north pole. So we are taking the two pole machine. Now how the flux is going to be, it is going to originate from the north pole and it is going to end at the south pole. The actual machine is like this, right, in a cylindrical manner. So that we have represented in a straight line. Okay. Now if you draw a line in between across the north and south pole, we can take that as the direct axis. Okay. And if you draw a line here, that you can take as the quadrature axis, or what we call as the geometric neutral axis. Okay. So you can represent, this is the direct axis, here we have, and in between both of them you have the q axis or the geometric neutral axis. Now the field flux we can represent as this. See, under the pole face it is going to be high, and after that it will keep reducing. What about under the north pole? Under the north pole it is also going to be high, but it will be in the opposite direction like this. Okay. At the quadrature axis it will become 0. So you are going to get the field flux like this. Okay. It will be something like this. So this we represent as phi f. It is maximum under the pole faces and 0 at the q axis or the geometric neutral axis. Next, if you talk about the armature flux is going to be 0 at the direct axis. This is because the flux due to individual conductors, it will cancel out. So from here it will go on increasing, and at quadrature axis it will become the maximum. So here we are talking about the armature MMF, not about the flux, because flux is going to be slightly different. We will see why. We know that B is equal to mu times H. Now magnetic field intensity H, it is not dependent on the medium, whereas magnetic flux density is going to be dependent on the medium, because mu is a quantity that will change with the medium, right? Now MMF is proportional to the magnetic field intensity. So this what we have drawn here, this is the armature MMF, and this is the structure because it is not dependent on the material. But what happens to the flux density at the quadrature axis? This is the quadrature axis in between the north and south poles, right? What is happening there? There is more amount of air gap in the flux path. That means the reluctance is going to be higher, or the permeability, we can say it is lower. So the flux density is going to be lower as we go towards the quadrature axis. Okay. So overall the resultant you can take something like this. It will keep on increasing till the pole is present. When the air gap starts, then it will start reducing, and then again it will decrease. Okay. Similarly here it is going to increase till the pole is present, and then it is going to decrease. Okay. So this is the way in which the armature flux is going to vary. So this we will represent as phi A. You can note down a few points here as well. The armature flux phi A will be 0 at the center of pole face, and it should be maximum at the q axis, but it will take a dip because of the presence of air gap. Okay, so it should be maximum at the q axis, but due to presence of air gap it takes a dip. And what about the armature MMF? This is not dependent on the medium. Okay, so armature MMF, however, doesn't depend on medium, so it will be maximum at the q axis. So it is maximum at q axis. So finally, the resultant flux you can represent like this. So compared to the field flux, you can see that on one side it is going to be a little less than field flux, on the other side it's going to be a little more than the original field flux. Okay, and one more point that you can observe here is this here is the quadrature axis. At the quadrature axis the field is not becoming 0. Why is that the case? This is because of the shift in magnetic neutral axis. Okay, so this is the resultant flux. If you take the resultant MMF, then MMF it is going to go a further up high. Okay, something like this, because it is not dependent on the material. So this green color is the resultant flux and this blue color is the resultant MMF. Okay, so note the difference. So you can write a few more points here. Magnetization increases at one pole tip and demagnetization occurs at the other pole tip. Also, what is the other point? The resultant flux is not 0 at q axis. This is because of the shift in magnetic neutral axis. And the second problem that obstructs proper commutation is what? The inductive nature of the winding. So what will happen because of the inductive nature of winding? Inductive nature means the winding will have a appreciable amount of inductance associated with it. In order to understand this problem, you have to go into a little more depth regarding the commutation process. So we will take the commutator segments once again. Say the coils we represent like this. Okay, so one coil is connected between two commutator segments. Now the brush, if we take it to be at this commutator segment. Okay, so this is the brush. So here we have the commutator segments, here we have the windings, and here we have the brush. Next, what we will take the direction of rotation. So direction of rotation, let us say this, the commutator segment is moving to the left. Okay, this is direction of motion of commutator segment. Now what is happening? The current also, we should, let us assume it to be a DC generator. So the brush should be collecting the current. So current will flow out like this. So that means this coil will give some current, this coil will give some current, because there is symmetry. If you can take this as 2 times some I, then each of the coils is giving the current I. Now you can see that in this coil the current is flowing from left to right, and in this coil the current is flowing from right to left. Okay. Now as the direction of motion, as the commutator moves in this direction, the brush will stay as it is. The brush is stationary, right? Commutator is the moving part. Here we have an intermediate position that I have shown. Okay, so brush was initially at this, we can name these. This is A, B, C and D, let us say. So this is A, B, C and D. So initially commutator segment C was connected to the brush. Now it is slowly moving so that the brush will now be coming towards D, right? During that time, the coil, this is the coil connected between C and D. Initially the current was from right to left. By the end of commutation, the current should reverse. Okay, and during the commutation this change is taking place. From plus I to minus I, there is a transition of current, and this change should occur within the commutation time. So what is the commutation time? It is the time taken for the brush to be starting from this position to reach this position. The brush should finally come here, right? So here we have A, B, C and D. Okay, so the brush, it has started from this commutator segment, it has moved like this. Brush is not moving, remember, the commutator is moving. So this is the final position. Okay, so the time that the position changes from this to this is called as the commutation time, and within that commutation time this transition should happen. The expression for commutation time, this is given by Tc is equal to Wb minus Wm by Vc. Okay, so what is Wb and Wm? If you consider the commutators segments like this, okay, so the brush width doesn't exactly have to be equal to the commutator segment width. So this brush width we take as Wb, and Wm is the width of this insulating material. Now this is the starting point, because the brush is just starting to touch this other segment, right? Now what is the ending point? Once again, if you take the commutator segments, this is the separation. Now once the brush has finally let go of the connection with this commutator segment, then it is the end of commutation, that will be here. Okay, so now what is the distance that is covered here? This point, if you take, it is starting from this point, right? From this point to this point, what will be the distance, right? This distance is going to be Wb minus Wm. Okay, so that is the distance covered, and it has a velocity Vc. Vc is the velocity with which the commutator is moving. Okay, so distance by velocity is going to give you the time. So that is how we got the commutation time. Now the change of current from plus I to minus I within this commutation period, that value, if you find for practical machines, it is going to be quite high. Okay, so di by dt is going to be very high. Okay, what is di? This is the change from plus I to minus I, and dt is the commutation period Tc. Okay, so if this is very high, then what is the effect? Even a small inductance of the winding is going to lead to a huge voltage drop. We know that the voltage is given by L di by dt. So if di by dt is very small, even with a small amount, even if di by dt is very high, even with a small amount of inductance, the voltage drop is going to become very high. So when this voltage is high, then what is going to happen? Sparking will occur at the brushes. Okay, so this is also sometimes called as the inductive kick. Okay, so this is the problem with the inductance of the winding. So we discussed two effects here. One is the armature reaction and other is the L di by dt voltage, because of the inductive nature of the winding, even if it's a small inductance. Now armature reaction, it has two effects. The first effect is shift in magnetic neutral axis, and the second effect is the weakening of flux. Both are which we don't want. Okay, and the shift in magnetic neutral axis, it is going to lead to improper commutation. Okay, and what about L di by dt voltage? This will also lead to improper commutation. Okay.